Hello, folks. We can get started, I think. For the record, I always like to start my lectures with some sort of really pretty astronomy image that has something to do with the theme of the class that day, because we're very lucky in this field. We're very spoiled. We have a lot of very pretty pictures to share with the world. So just to show you this one, this is called a map of star trails. So if you expose on the sky for a very long time, you start getting these circles as the stars move in the sky. We're going to spend a lot of time today talking about how things move in the sky. So yeah, a little bit of a sneak preview there in case you're wondering why there's always these images at the front. It's always to set the mood or something like that. With that, today's plan is we're going to talk about the solar system by the first thing we do is, we can take observations. So the first thing we need to discuss is motion in the sky. What do we see about, the most obvious thing in the sky, our sun and our moon and the planets, and how do they move in the sky? Various solar system models. So geocentric, heliocentric, is the Earth in the center or is it orbiting the sun? And then we have observation and models that we can use to test those two different models. We're going to do our activity phases of Venus, which is going to inform us. Do we live in a world where everything revolves around us, or do we live in a world where everything revolves around the sun? And you guys are going to run the experiment yourselves and hopefully reach an interesting conclusion. We're going to start off with a little bit of a discussion for a few minutes. Imagine you were alive 2,000 years ago, so we have no cell phones, no TV, nothing except looking up at night. And the stars are beautiful because we have no electricity. And you're regularly looking up at the sky. How do you think you could detect planets in the sky? And how do you think you could maybe tell them apart from stars? So you can see planets earlier than other stars, and some planets are, in fact, brighter than other stars. Mainly Venus and Jupiter are basically the brightest planets there are out there. Mars can become very bright when it's very close to Earth. Stars can also have colors, so that's maybe not the best one, because some stars can look very red, for example. That's, you have to take the stars astronomy class if you want to learn more about that. Planets don't twinkle. I don't really like this one because it has to do with basically the size of Jupiter in the sky is a certain size, so technically it doesn't twinkle. But if also you're in a city and the atmosphere is just very turbulent, you'll see it twinkle. So that's getting down into the weeds maybe. But I've heard this many times that planets don't twinkle and that's how you can tell. And that's really, unfortunately, not very true in my personal experience. However, one important thing to note, though, is yes, planets move in the sky. So I'm an astronomer, as you guys know. I'm an unusual astronomer because I actually know my constellations. You don't actually need to learn that anymore to know this job. I just didn't, when I was a teenager, very interested in astronomy, I was a real nerd and learned all my constellations. So I look up, I know everything in the sky. I no longer look up when the planets are where, but I'll look up and I'll be like, oh, that must be Jupiter because there's a really bright thing there. It wasn't there, last year when I was looking at this patch of the sky. So things like that. If you look at the sky and you know your constellations, it is actually pretty obvious for, the innermost planets. Mercury, Venus, obviously we're on Earth. You can see that one very well. Mars, Jupiter, Saturn. Those are the naked eye planets that we can see with our own eyes. So how do we know this? So first of all, we're going to discuss what is called the celestial sphere. So at the start of this lecture, I showed you guys these star trails. So as I said, this is an exposure for the entire night from a certain patch of the sky, apparently in Big Bend National Park in Texas. So each one of these tracks is an individual star. So you can see it here. And then it goes upward. And this is the motion of that star over the course of several hours or over the course of the night. So it's tracking in the sky. And they're all tracking, as you will note, around the same patch of sky, which is here in the center. Does anybody know what might be at the center here? Yes. Yep, the North Stars. The North Star is not exactly on the center, but it's very, very close. So it's this bright little one here. And you can say it's not really moving. It's within a degree of true north. So good enough if you're lost in the woods or something like that. So with the scientific method, what we can think of is, okay, we're going to answer questions about our solar system. We have these observations. The first observation that we have is there are stars up there and they're moving in tracks is the way to think of it. So what does this actually mean is, a question that you might ask yourself. And then we can, think about hypotheses of what this means, how the stars are up there. And then we can do experiments. So we can basically look at stars, how they move, look at maybe other things once we think we understand the stars and how they're moving relative to those stars. So the first thing I want you to do is imagine that, the Earth is in the center of an imaginary sphere. The stars are basically fixed on that sphere. So in this image, you can see here's the Earth. Here are all these stars. And the sun, moon, and planets are not on the sphere as well, but they're not fixed. And they're going to wander. So I'm going to show you guys how this works. So here's, 1 month. We look at a normal month. The sun and all these planets these dots are over here and things like that. As I said, the planets and the sun are moving over time compared to the rest of the stars out there. So planet actually means a wanderer. What basically ancient astronomers who looked at the sky, our ancestors thousands of years ago, they saw that there were a handful of these naked eye things up there that were moving relative to all the other ones. So they were the wanderers. Of course, they didn't really know what they were. They named them after the gods in all sorts of different languages because obviously gods are the only ones that could be moving around up there, right? Can't be any other planets. So the sun, though, is obviously the most important thing that we track. It is why we are alive and everything like that. So the sun moves across the surface of the celestial sphere, and it makes a complete path once a year. So, you start at the bottom, you go upward over time. That is probably, hopefully, fairly straightforward to understand. The other way to think of this is the sun, as it travels, is going on a specific line. The specific line here is not in line with our equator. It's a little bit off by about 23.5 degrees. We'll be discussing this more in the future. But this line is a very important name, and it is called the ecliptic. The ecliptic, for those who know their zodiac and zodiac constellations, runs actually through all those zodiac constellations. That's why those are important constellations. And all the planets as well run through the ecliptic over time. The ecliptic is basically a projection of the plane of our solar system, is the way to think of it, into that celestial sphere. So you're never going to see a planet wandering up, say, toward the North Star, which is, all the way up here. Planets and everything, and the sun and the moon are all going to be in this ecliptic plane. So, as a quick check to understanding, the moon also moves across the sky near the ecliptic. How long does it take the moon to make one complete trip around the celestial sphere? Yep, exactly. So the moon orbits the Earth roughly every 28 days is the rough period of a moon cycle. So it's not quite, unless it's February. It's a little bit off, but close enough. So yes, 1 month. So the planets also, as I said, travel close to this ecliptic. And I will show you an animation of what this looks like. So this is, if you're an observer, this is set up for Eugene. You're the observer there in the center, and this is your celestial sphere going overhead. You can see the time down here on the lower right. So this is Pacific time tonight, middle of the night. If you look up, you're going to see Saturn setting. You're going to see that's not the moon. Come on, there must be some morning planets. Jupiter's up here in the morning sky. You're going to see Venus is the morning star right now in the sky. And then, yes, it's going into daytime. You can't see this anymore. But so, as I said, these planets are also going to go at the same ecliptic. There's some other motion, though, in the sky. So the sun is pretty straightforward. It just marches ever forward. The moon's also pretty straightforward. It goes, on its path in orbit. Planets, though, are a little bit different. If you watch a planet for a very long time, you're going to notice something, which is that planets don't always just march forward. If you watch a planet, sometimes, as you can see in this GIF, it will go forward, it will loop backward, and then continue going forward again. This is called retrograde motion. Is what this actually means. Here on the right is an illustration of if we were to trace this out over time. So as you can see here, Planets, though, are a little bit different. They're not behaving the same as the sun and the moon in the sky. So if you ever wondered what it meant that Mercury is in retrograde, this is what it means, but no, it has no impact on your life or your love life or anything like that. So with that information, and keep in mind, pre-telescope, this is pretty much the information you're going to have, the information you're going to notice in the sky. We can have some solar system models that we could make up. And the first model, which existed for thousands of years in astronomy, and most cultures around the world had a similar model to this in some form, is the Ptolemaic model, or geocentric orbits. So this is the rough idea that the Earth is in the center, and then there are planets and the sun and everything orbits the Earth. It's called the Ptolemaic model because the ancient Greeks were very good astronomers. And so Apollonius and Hipparchus were the first ones to figure this stuff out. But then over time, Ptolemy in 147 AD, he wrote the book about it. So that's why it's called the Ptolemaic model. However, if, we just have these spheres and they're going around, why would you have these retrograde cycles as well? They had to think up some solution. So the solution the ancient Greeks thought is the Earth is in the center. They didn't think that they were planets. They thought that basically you had, a giant celestial sphere with all the stars outside. It was fixed. Then you had inside these other spheres. So you had a moon sphere, a Mercury sphere, Venus, Earth, Mars. And the planets were basically in those spheres, and those spheres were moving. Within those spheres, then, everything could also move in a circle called an epicycle. So you could imagine you have a ball turning, and then on the surface of that ball, you're spinning around like a little top or something like that. So that is what an epicycle is. Yes, it is a complicated system, but to a very low level degree, it does explain retrograde motion that you might see. So, however, then there's another model, which is called the Copernican model, which is, of course, that the sun is in the center of our solar system and we orbit around the sun. Of course, the moon orbits around the Earth. And it's called the Copernican model because it was proposed by Copernicus, a Polish astronomer, in the year 1534. You do not need epicycles in this system. We just have our planets with the sun at the center. So how does this explain retrograde motion? If you have a Copernican model system, so here's Earth, here's Mars. So we have up here at the top that retrograde GIF that you guys saw earlier of its motion in the sky. The way you have to think of it is slower planets move backwards because we're basically cars on a racetrack. When cars are on a racetrack in a turn, they're going to appear to have different motion if you're on one car looking at the other car. So if you're looking from the Earth to Mars, you're going to, as you pass it, it looks like it's going to do a little loop-de-loop in the sky. And that is what is causing, in the heliocentric model, this retrograde motion. Here's a non-GIF version if you want to take a look at this, just to understand this a little bit better. So when we start out, we're both at A. Nothing is passing anything yet. We're here. Once we get to B, we're at the top of this model here. C, we're passing, so it looks like the planet slowed down, and then it swoops backwards for D as we pass. Then eventually it's going to continue on its merry way once we have passed that planet. So, I just told you we have these two models of the solar system. I think most of you probably know which one is the current accepted theory. But we're going to use this as a great way to test the scientific method. So we have some observations of the planets. We see that they're moving differently from the sun and the moon, and they're doing these little retrograde swoops and things like that in the sky. We have two hypotheses. We have the Ptolemaic model, and then we have the Copernican model. And then it would be really, really cool if we could do an experiment that tells us which one of these models is correct. And the way we are going to do that is actually by looking at phases of the planet Venus. So the goal here is to investigate both of these models to find out what predictions they make about those phases of Venus. So a quick primer on phases. We will be discussing the phases of the moon later in this course, but just for now, when something is completely black, you don't see anything, that is called the new phase, or if you have a new moon. If it's completely full, the full moon or a full planet or something like that. In between, if it's less than half full, that is a crescent phase. And if you have something that is between half and full, then that is a gibbous phase. So just so we all have the same terminology down. So I'm going to show you guys some simulations. We're first going to look at them together. Then you're going to work together and ask questions. We're going to have about 15 minutes or so for this activity. So first we have the Ptolemaic model, which I have the QR code for there. For later, I'll have this up and then you guys can scan it if you prefer. But just to show you, here we have the model where the Earth is at the center. Venus is on its sphere. It has its little epicycle thing going on as well. And then out here is the sun at a further distance. And now we can start the animation. And down here, you will see phases of the planet Venus as it is going around. So that's what we mean when we're testing this simulation. This is how we're running it over the course of several years. Now I will show you guys the Copernican model. So the sun is at the center. Venus is closer to the sun than we are. And then we have the planet Earth here. And we are going to start this animation. And you can see that there are also phases of Venus that we can see over time. And they are also changing at a different rate, I think it's fair to say, than in that epicycle model. Yeah, look at that. Okay, so let's talk about the Ptolemaic model. What kind of phases could you not get in the Ptolemaic model? Yeah, so it just wobbled back and forth. You never even got to 50% illuminated, which is half. So you definitely never got to gibbous, which is 50 to 100% illuminated. So that is a pretty big tell, I think is fair to say, when distinguishing those two models from each other. So you guys just did something that you could basically do because we live in the era of the telescope. So when we think of astronomers, Ptolemy, as I said, he was an ancient Greek astronomer. He lived between 100 and 170 AD, and he wrote or published his work on astronomy, the Almagest, in 147. Then, over 1,000 years later, Nicholas Copernicus, who was a Polish astronomer, on his deathbed, published on the revolution of celestial orbs, 1543. In 1543. The reason he had to wait till his deathbed is basically the Ptolemaic model and Greeks and the science that they had was canon at the time in the Catholic Church. So basically this is, how God ordained the heavens to work. We have these celestial spheres. The Earth is at the center, and that is why the Earth is important, is because we are at the center of all this stuff. However, the real problem is over time, the epicycle system didn't really work for many reasons as they were tracking things in the sky. So Nicholas Copernicus on his deathbed decided to be brave and publish something that was not really going to hound him because he would no longer be around, suggesting that the Earth is in the center of, the sun is in the center of our solar system. But it really was, a theory, a hypothesis that was not yet tested in many ways. So which one was correct until Galileo Galilei, who lived in the early 17th century, late 16th century. And he basically had something very important, which in this artist's illustration of him, you can see here, which is a telescope. So Galileo did not invent the telescope. That was actually Hans Lippershey, who was a Dutch merchant who invented the telescope in 1608. However, Galileo was the first person to point a telescope at the heavens. Now it seems very obvious to us, But basically, originally they invented telescopes because they just wanted to see ships coming up the horizon. So if you could see what ship is coming back first, that's really, really important. Things like that is what they were more interested in. So Galileo, he had this telescope, and then he observed phases of Venus and the moons of Jupiter in 1610 with this telescope. I should also emphasize to you guys, if you have a pair of binoculars at home and you've ever looked through one, those are more magnification power than Galileo's telescope. It was not a very good lens because there was very early time when they were doing these things. And yeah, so it's a very not good lens. If you have a pair of binoculars, you can do all these experiments or see all the things that he did pretty easily, actually. But so, okay, what do we have? We have our epicycles. We have these two models. And then we have this experiment. If we see the phases of Venus, we can see differences between the Ptolemaic model and the Copernican model. So what do we see? Well, it turns out we have drawings that Galileo did in 1610 when he first looked at the planet Venus. And what do people see? What phases do we see here? Yes, you can see all of them. Could someone say which model this is consistent with? Yep, so this was real direct evidence from an experiment that the Copernican model is basically what makes sense if you're looking at things like the phases of Venus and how Venus works in the sky. And then, so this is phases of Venus. If you run a simulation, you will also get the same thing as you guys saw in your picture, which is this model that the sun is in the center of our solar system. You have all these phases that you see for Venus as we go around. There was also not as direct evidence, but circumstantial evidence. So Galileo saw other things in the sky with his little telescope that also pointed to the fact that the Earth is not at the center of the universe. Side note, he also used his telescope to look at the sun and looked at sunspots. I do not recommend doing that with your binoculars or telescope, but he didn't know any better. One of the most famous things, though, Galileo also looked at were the moons of Jupiter. So Jupiter has over 100 moons. We're going to talk about that later, but it has 4 very big moons. They're called Io, Europa, Callisto, Ganymede. And they're so big that even with a pair of binoculars or, Galileo's little telescope on Earth, you can actually see them. You'll see a big dot where Jupiter is, and then you'll see these little dots around them. The second thing that's very cool about Jupiter's moons is they orbit fairly quickly. They orbit within 2 to 20-ish days, depending on which moon. So the closest one, of course, goes around Jupiter the fastest, then further out. So what Galileo did, here's his drawing. This is Jupiter in the center. And he noticed these bright dots. So like how you can see in this image here, these are the 4 Galilean moons. And he was like, okay, there's 3. Huh, that one moved. There's 3. Now there's only 2. Weird. 3, 1, goes down, 4. So what you can see here is he was basically looking at every single night at the sky, and he could see these moons moving around Jupiter. So what does this tell us? This tells us there are things, even in our solar system, that do not orbit Earth. So why should you believe that the Earth is the center of everything if there are other things orbiting other planets? So that's, as I said, not direct evidence that we live in a Copernican model system, but it is pretty darn good circumstantial evidence that solidifies the argument. So just to summarize, what are the learning goals that we had for this class today? So you should be able, hopefully, at the end of this, when you look at the lecture, things like that, describe how the planets, sun, and move on the sky differently from the stars. Explain how the geocentric and heliocentric models explain planetary motion, especially that retrograde motion. Why does it look like the planets are doing these loop-de-loops in the sky? And you should also be able to discuss direct and circumstantial evidence for the heliocentric model.